Hi everyone. Let's compare the presentation. Okay. Thank you for your attention. The title of this presentation is Design of Analysis of Dissipation, Preservation, Models for Higgs boson equation in the de Sitter space-time. I am Armando Gallegos, and this work is made in collaboration with Luis Fernando Muñoz Pérez and Jorge Macías Díaz. So let's continue with the presentation. This is the table of the contents. Firstly, we establish the problem statement, and after that, a numerical methodology, structural properties, and computer simulations. Okay, here we can see the general Higgs boson equation in the de Sitter space-time with initial boundary values. Here we can see the partial differential equation and the initial boundary conditions, where the symbol delta represents the spatial equation and the nabla symbol represents the gradient operator. With this model, we can establish the energy, which can be provided by this formula, and the local energy density can be expressed in terms of the Hamiltonian, which is given by this equation, and the rate of change of the energy is given by this last equation. We want to express this problem in terms of the radially symmetric solution, where the variable r is the Euclidean norm of in the space of X, and phi is a solution radially symmetric of the system. So the problem can be written in this form, but we perform the following transformation. So the Higgs, the boson-Higgs equation is written in the following form with these initial boundary conditions. So the total energy density, and the energy rate of change are rewritten in terms of this new variable, psi. Okay. The main idea of this work is to provide a numerical method in order to solve the problem presented previously. So we consider this regular partition for time and space, and a subintervals for time, and m subintervals for space. And we define the following discrete operators, which can be expressed in the usual form. For the linear operators, we establish the inner product and the general P norm in this form, and this discrete nonlinear operator in order to express the difference for the function f in the original problem. Okay, with these definitions, we can propose the finite difference scheme for the main problem in terms of this system of discrete equations. Here we can see the three-step implicit discrete model associated to the finite difference scheme proposed. So the energy and the energy density can be expressed in terms of these discrete operators, and the discrete energy rate of change can be written in the following form. It's a little bit large, but this is the expression. Okay, let's review the structural properties of the numerical scheme. Firstly, let's review the solvability of the scheme. So this theorem is based in terms of the induction and the Brouwer fixed point theorem. Okay, let's start with the initial data. So we assume that psi n minus 1 and psi n can be calculated already. And we define the component SG in the following form. And let's perform the following inner product. And as I comment, we will use the Brouwer fixed point theorem. So let's perform the inner product of the function S and psi. And taking account the function f is a smooth function, so we can say that there exists a constant k that satisfies this inequality. And this inequality is well known, so we use it. And rearranging terms, we can associate the red terms with the parameter lambda, and we use the Brouwer fixed point theorem, and the theorem is proved. About the consistency, the theorem is based on the Taylor's theorem. The main idea is to compare the continuous operator with the discrete operator. So we establish this difference between the continuous operator and the discrete operator, and use the triangle inequality, and we establish the parameters C1, C2, C3, and C4 using the Taylor's theorem, and the theorem is proved. Let's review the stability. So for the stability, we will use the Grunwald's inequality given by this lemma. So the main idea of this theorem is to associate this part of the inequality with Wn, and this part of the equality with rho, corresponding to the Grunwald inequality. Let's start performing this inner product. And we perform the inner product explicitly. And rearrange our terms, and using the main value theorem, we associate these terms in red with the raw and rearranging terms. We use the Gromwell's inequality, and the theorem is proved. Okay, as a corollary of this theorem, we can establish the uniqueness of the scheme. So let's suppose two solutions of the scheme, but with the same initial conditions, and let the epsilon as error between two solutions. And we use the stability, which is guarantees that this inequality is satisfied, but the initial data are the same for the two solutions, so the right part of the inequality is equal to 0. So all the errors are equal to 0. Therefore, the solution is unique. Okay, the theorem about the convergence can be proved using the same arguments previously presented. So we omit the demonstration. Finally, I will show you the computer simulations. For that, we established the following definitions of the function b in order to define the bubbles in the simulation. So we can see the solutions. In the first row, the solutions for the problem with these parameters and initial conditions, and the density of energy in the second row. Here we can see the solutions for another set of the parameters and initial conditions. And here we can see another type of solutions. Okay, finally, I want to stress that this work is a continuation of the previous work already published in these papers. So the idea is to show that the boson Higgs in the de Sitter spacetimes is a very interesting and important problem now. So that's all. Thank you for your attention. Thank you.